how far are you? So we should have some condition under which we should say you are far. All this in relation to where your transducer face is, right. So when you say transducer face, you can clearly intuitively guess the influence of this face, right, is going to be the distance. If I have a bigger face, I will probably have its influence farther region. If this is a smaller face, probably I will have the influence over a smaller region. So this near or far, you can intuitively guess is going to be in relation to the size we are talking about, right. So I mean, in a very colloquial example, if I have a long arm, right, I can reach you. So you are near me means if I can hold you, right. So it is in relation to whether you are near or far depends on what is my reach, right. So like that, if it is a near field or far field depends on the surface. If this is a larger surface, maybe I will have more influence over a deeper region, right. So in that sense, you have to define your far field in terms of the size of the aperture, okay. So your z, the distance, if it is greater than d square by lambda, okay. What is your d? D is just a dimension. So if it is circle, for example, then it is a diameter. If it is a rectangle, you could take the the largest diameter, right. So here face, basically this is to do with your dimension of your aperture. Circle is simple, I can just use the diameter. If you have something else, you can still consider that it is the maximum of the dimension of the face that you are using, the transducer shape, okay. So if that is the case, why are we interested in this approximation if z is far greater than your d square by lambda? In such a situation, turns out that this guy goes to 1, this exponential of this goes to 1, okay. So then what happens? Oh, you are left with S naught and then this exponential. Not only that, look at this exponential little carefully. What do you see? K, okay. K is what? Oh, K is your wave number, is your 2 pi by lambda. Oh, so e power j 2 pi by lambda. So quickly you will recognize you have a form where x naught, y naught is there, you have exponential, your running variable is also x naught, y naught here. So you have a x naught, y naught here. So this 2 pi by lambda is j 2 pi, right, x. So this x, this lambda can go in, right, you can 2 pi by lambda, j 2 pi, x by z lambda, y naught, y by z lambda. Doesn't this look very familiar to you? We have done this several times. What we have done is, oh, f of x comma y exponential of j 2 pi of ux plus vy dx dy. What was that? Oh, your Fourier transform, 2D Fourier transform. So this is nothing but a 2D Fourier transform of this guy. That's what this is. Fantastic, right? So you will quickly recognize what you have here is 1 by z, this guy times this whole thing is nothing but a Fourier transform, right. Only thing is your u and v you have to recognize, so this was x naught and y naught. So your x by delta, x by lambda z, y by lambda z. So you have a spatial frequency ux vy is what we wrote in our general formulation, right. So you can recognize what is your u, what is your v. 1 by lambda z, 1 by lambda z is here, right. So what you have in some sense is very revealing. I mean, this, what this is saying, what is this S? What is this S? Oh, S is your aperture, right? Shape, something to do with your shape of the transducer. What this is saying is your directivity, what you are seeing in the far field, the pressure distribution in the far field is going to be related to the Fourier transform of this shape. So, if I have a particular shape, I know the distribution that is going to happen in the far field. It is going to be following a Fourier transform of this. That is a very powerful, powerful concept. Okay, so please spend some time to appreciate what is happening here. You may have to read it multiple times before to get that joy as to, okay, I do see what is happening. So, I will spoil your party by showing some examples, but clearly at this point you should be comfortable that we talked about thickness mode that determines your frequency, and then the shape and size both have a role to play. The Fourier transform of the shape is going to give you the far field pattern, right? The pressure distribution in the far field, the shape of that, right? That pattern is mathematically described by as the Fourier transform of this shape, and the size of this is also going to determine where this is going to be applicable, whether you are in the near field or far field. Okay, so you see the size and shape of the transducer determines how this pressure is going out and where all you are getting the reflections from and the sum total that you are getting. Okay. So, just to put that back in our parent equation, R of t is all from before. I have just written this because we had a q square, remember. So, the q is now we recognize that as, so you have your s square. Okay. So, this is a very powerful equation. In the far field it is little straightforward because you know the distribution is going to be determined by the Fourier transform of the shape of the aperture. Okay. Otherwise all of the terms are from before. Okay. So, just to circle back, complete this idea. So, now you understand what I meant. So, when you have this excitation from this crystal here, say in this example it is a circular transducer. So, you notice the beam pattern. So, if you take a cross section, right, if you take a cross section, so if I take a cross section there, right, if I am to do the intensity there, you are going to have, so I am just doing a rotation so that it is easy for me to draw. What you are seeing is going to be predominantly, here you are going to see intensity map like that. This is in the far field. If I do that in the near field, what is going to happen? Sorry, right? If I do that there, how is the profile going to be? Oh, it's going to have up, down, something like that, right? Clear? So, if I take the profile along the center, this is going to be the fluctuation. So, that is what we had, right? They were captured in an equation. Here we have a plot of that. Okay. Good. So, what we will do now is recognize two other important ideas. One is this divergence, right? So, that means it is diverging is what we, so angle of divergence is a parameter, and what is the idea in this beam? See, what is the disadvantage in divergence, right? In imaging, what are we supposed to do? Oh, in imaging we are supposed to know the lateral also we should have good, right? In the axial direction is fine where the high frequency wave is going, but in the lateral is related to your beam width. So, we need to, so divergence, right, we should be able to know what is this divergence. So, divergence is not good, okay, because you are loosening up your lateral direction. If you have a point, it will spread more in the lateral direction. Point spread is you are going to relate your both contrast and your resolution per se. So, what we will do is we will just quickly show some. So, this is your from a rectangular transducer, what I showed before circular, this is a rectangular, and you see the similar trend in the near field. What is a near field or far field? Remember, go back, we just made some formulations, right? If it's circular disc, d square by 4 lambda, so 2 times that, so d square by 2 lambda. If it is a rectangular transducer, shaped transducer, d square by lambda, right? So we had all this in the previous module. So when you go, you see this general nature. There is a lot of fluctuation in the near field or close to the transducer. As you go farther and farther, it becomes much smoother field. Okay, irrespective of the shape of the transducer, the general behavior is same. So this is one another important way of explaining or communicating what we just covered, which is what is called as an antenna plot. So typically, because you are talking about divergence, you are talking about angle. 0 will be exactly straight of the transducer, right? But more importantly, it is not just doing 0, it is spreading out in plane and elevation, the perpendicular, both. But in imaging, at least we are interested in plane, how it is spreading in the other direction. So if you see an image, right, if you see an image, if this is your depth d, right, skin, and this is depth, this direction is fine, that is your axial direction. But what we are interested, right, is spreading in the other direction. So we are talking about this direction. So if I have to just plot, right, this is my transducer, right. So typically how do they represent? They represent it in terms of antenna plot, where you see that there is an angle of divergence. You can calculate that. You can calculate the angle of divergence using, right. So you have your main lobe. Remember how I showed there is a fluctuation in the near field, right? You had main lobes and side lobes. So you can see all that here. So this is your, if I am trying to insonify only front of the transducer, unfortunately because of the size and shape of the transducer, you get different pressure experiences in the field. So there is a pattern to it. So we call it field pattern. So your sin phi of d, so phi d angle of divergence is sine inverse of, so what you recognize, what is this A? A is your radius, d is diameter, A is radius of the transducer. So that you notice there is an inverse relation. So if I have a larger A, I will have smaller divergence, right. So that is something that is a important message that you should remember. So if I have a larger aperture, larger transducer size, then I can probably have less divergence. I can, right, that is an important aspect. So that is for circular. Similarly for your rectangular, you can get your function to be like this. What is this? Don't get intimidated. It's actually very, very powerful, that we already covered an important. What was this Q we talked about? Oh, it has to be some Fourier transform of your x, sorry, of your s. When you look at this, what do you see? Oh, sine of some quantity by that quantity. Have you heard sinc? Sine theta by theta. Oh yeah, yes, sinc. So this sinc has, so this is rectangular transducer. If you have a rectangular transducer with different dimensions, right? So your B is your width, for example, or square transducer. So how does, what is your, so this is 2 dimensions, square means. If it is a rect function, what is your Fourier transform? Sinc, right? If you have a rectangular in one, right, in time domain, in frequency domain, that will be a sinc function. You have done this Fourier transform before. So now you have 2 surfaces, right? So surface is 2. So you have rectangle in one, rectangle in other. So that is what is your square, for example. Then you have to have sinc for one dimension, sinc for the other dimension, because Fourier transform. Okay. So it turns out that that is also, so here, that's why I think I made a mistake. So one has to be h. So the x direction is B, y direction is h. Okay. So, this is your x direction, this is your y direction, z is in and out of the right the plane that is coming in. So, clearly if you have a rect function, right, if you add a rect function, you have sinc, right, sinc is your transform, Fourier transform. So, here you can see this as sinc in one direction, sinc in other direction, that is why it is, oh, I have a rect here, sinc square, right. So, look at the beam pattern. So, wherever it is, right, you have two of them because one is for one sinc function, the other is for the other sinc function. You notice the divergence is different in the different directions. So, in plane, right, when it comes out it is 3D, right, if you do it is 3D. So, you can have lateral and elevational. Okay. So, each of that how it is determined by that respective dimensions h or b. So, to summarize, this also exhibits a similar case to circular with main lobe and side lobe. So, the problem with all of this, I will talk about this further when we go to the imaging aspect explicitly, but the side lobe is undesirable. I am thinking I am sending pressure in front of the transducer, but when it is leaving the transducer, it is not just hitting the object in front of the transducer, it is also hitting, right, with some pressure levels, it is also hitting at different angles. Okay. So, when you are receiving it, you are going to get echoes from, because of these pressure it is hitting in some other object in a different direction, but you have no way to tell that. What you get is a surface integral. Okay. So, you have to recognize here as well we could get the the divergence angle we talked about, right. So, we can here also we can get, but for two directions. So, you can get for x direction, you can get for y direction. It is a similar idea, it is a sine inverse of lambda by h or sine inverse of lambda by b. So, clearly this pattern is asymmetric. In circular case it was symmetric and therefore we just got sine inverse of 0.68. So, something that I probably missed. Circular also same, right. When I said rectangular you got sinc. When I have circular disc, the Fourier transform of that is a Bessel function. So, Bessel function also has a standard, right, form. So, you can calculate what is the zeros, the first zero crossing in your Bessel function, right. First zero crossing you can define as your main lobe. Okay. So, that is how it was done there, but it was circularly symmetric. So, I didn't mention that, I forgot. So, here it becomes, so it is symmetric, whereas here it is not symmetric. The divergence is different in the different directions because the dimensions are different. One is b, the other is h. So, the inverse relation still holds good, that is the larger the dimension, less divergence in that direction. Okay. So, that is important. So, in this case for example, taller than wider transducer shape will yield a wider than taller pattern. Okay. So, this is very important. Take home message is, if I want divergence to be less, I should have large aperture, but is there downside to it? Well, when we cover imaging, we will explicitly handle that, right, we will address that, but even before that, in some sense you should intuitively start to think, okay, what is the good? If you have large, we can probably divergence is less, but what is the disadvantage of having large transducer? Well, we talked what we are receiving is a surface integral. So, that means you are going to get signal from a larger volume, right. What is our objective? Oh, eventually we should be able to precisely say which scatterer is located where. The R distribution should be as fine as possible, right. But if you are going to use this, you are going to get one net sum, right. So, in some sense you can already start to feel the problem. Okay. I want it to be small, divergence should be less, So to have divergence less, I need to go for a larger aperture, but if I go for a larger aperture, then even if it is not diverging, the volume that it is going to insonify is large already. So you will get a signal from a large volume which is integrated and you get one value. So in some sense there is a trade-off. Okay, we will explicitly cover that as we go forward. One last aspect, again, if you have a rectangular, so you can think about the transducer. If you take one cross section, if you are going to have a hard, right, transition, very similar to your windowing concept that you know in your probably first level signal processing course, right, when you do filter design. So if you take a rectangular window, you will have more ripples, right. So what do? Oh, they do some windowing, hamming, you would have heard those terms, right. Similar thing is applicable here as well. So if I have a transducer which has, oh, it is only crystal is here and it is cut such that there is nothing outside. So it's a hard boundary. If you have a hard boundary, you're going to have lot more ripples. How do I smooth it? Window it, shape it, right. You can do window it, shape it. So we will talk about that. Two things to notice here is the fluctuation is reduced. Actually we saw this earlier also, but this is little less cluttered. So in the near field, right, this is your wavelength, this is your transducer, this is your how far are you away in z axis with respect to with your dimension. So if you are close, you have a lot of fluctuation. As you move away in the far field, it becomes a smooth pattern. Okay. So we will get back to this first slide where we had, okay, you have a geometry, d is your diameter of your crystal. So shape and size, you have a beam that is retaining its width same as your d until certain point. After that it diverges, we can calculate phi d. So based on this we define a near field region or a far field region. So now if you have another transducer with a larger, say, because that is what we covered, inverse relation. So if I have a larger, so if I have another transducer A and transducer B, if a transducer A is much larger, oh, the divergence is less, right, that is what we saw so far. So smaller transducer diameter, then it starts to diverge, so divergence is more. So divergence is less, divergence is more is okay, but then you notice if it is divergence is less, right, here you notice that this extra space, so much volume you are going to insonify. So your ability to look, because at the end whatever you are going to get as R of t you are receiving, you are going to say came from location 1, location 2, location 3 along the depth, that is what you are going to say. So it will be good for you to also localize it in this direction. But if you have a less divergence, right, having a larger dimension transducer, then you are compromising on that localization. Okay. So we will beat this little bit further, but now what we will think about is, okay, given this transducer, can I achieve both? Can I have a larger transducer, but can I also have a smaller beam width? If I can do that, then that solve my problem. Okay. So so we need to talk about focusing. Before we do that, let us just complete this beam profile that I was talking about, right, your rectangular function, hamming window. So you could do that here. So what we can do is have the crystal, but make sure that the crystal is not excited, you have some weighting. So the center point gets the maximum weighting. As you go towards the end, you have less weighting, and this how much weighting you give can be determined based on your window function. Okay. So you could come up with a material. So basically this is sound. So I want only the center to contribute, sides to less contribute less. So I can have a sound absorber, more sound absorber at the corners and less sound absorber at the center, and I can have a profile. of that. It can change from no absorption to high absorption in a, say for example, exponential fashion, which is kind of your windowing. Okay, so if you do that, you can make, so instead of this rectangular, I can profile it, right. I can come up with a material, say sound absorber, right. So that's an easy one to visualize, at least for you. So you can come up with some material on front face of the transducer, where it will preferentially allow only more from the center. Then you are going to smooth this out. If you smooth this out, you notice the profiles are lot smoother here than here. So this is a technique which we call as apodization. Okay, this is very similar to your windowing that you would have studied. It's just the jargon is slightly different because the context is different. So now the last point that we need to address is, can I then make the beam profile or beam pattern as narrow as possible? So how do I reduce the width of the beam? Okay, how do I reduce the width of the beam? So I don't want divergence, at the same time I want to reduce the width of the beam. How will I do that? Well, you could use a lens, a focusing lens. Is very similar to how you do lens in optics, right? So we could have a lens in this case as well, but this lens we call as acoustic lens. Instead of optical lens, you have acoustic lens. So what do we mean by that? Oh, this lens will have its own material properties. So CL, right? And then you have, this is your medium, and it has a radius of curvature, right? Radius of your lens RL. So this is your transducer, the pink or orange that I have. At the front of the transducer, the flat disc, right? It was a flat disc. In front of that, I could have a acoustic lens with certain curvature RL, and that can be designed to where you want your so this is your length of focus, where you want your beam to be as narrow as possible, right? That is your focal spot. So there is a length of focus is the location Z at which this lens is going to help focus the beam. So all the acoustic pressure coming from the surface of the transducer, all of them are going to be focused to a smaller region here. So it will become the narrowest, right? The divergence we talked about. So instead of divergence, before it starts to diverge, I want to make it to as small a region as possible in the imaging plane. So the only thing is here, instead of optics, I mean as opposed to optics, a shape, if you look at it, you are talking about see, there also it's the same thing, right? We have phase velocity, but then here we are talking about acoustic phase velocity, and therefore this ratio and the shape, the converging means we will have a concave face here. A converging positive lens will have a concave shape here, but otherwise the concepts are very similar. So what this does is, you can use the same Snell's law. If you do that, you can get your L of F, length of focus, to be given the geometry, right? You have your RL, so you can get RL by 1 minus Cm by Cl. So this is fine. What are we interested? What is the at LF? What is this? Oh, this is where the beam profile is narrow. What is your beam profile or beam pattern? Oh, beam pattern was my Fourier transform of the shape of the transducer, right? So if you recall, we had a Bessel function if it is circular, we had a sinc function if it is rectangular, right? That is the profile at that Z far field. So if I want to do this, what is going to happen? Oh, I could just substitute, right? So let's call this LF as some equation F1. So what does this L do? Sorry, what does this lens do? Oh, it transforms position. More importantly, for example, if it comes and hits at an angle, this angle is transformed to position. That's what this lens is trying to do. Okay, so if we do that under small angle approximation, right? Small angle approximation given this, so this is your FL, right? idea is it is going to spread, reduce the spread. So if it is spread out, what is the lens going to do? It is going to bring it in, right? So that means it is going to kind of do a transformation of angles into positions. So if you look at this geometry, you can get your sin phi, right? This is your LF, this is your XL. So you can get sin phi is XL by LF. So if you do a small angle approximation, we can essentially write, right? We had our sin phi for an angle of divergence before, same thing, but now we will substitute for sin phi to be XL by LF. Okay. So your XL by LF 3.83 by Ka, this is what we had for the circular transducer. Okay. So there we just left it like that, sin phi d is equal to 3.83 by Ka. So phi d is equal to sin inverse of 3.83 by Ka, that is where we left for the circular. Now we are having a lens, and the lens helps us with the transformation. So the sin phi d or sin phi can be approximated to XL by LF at the focal. So you can substitute, you can get XL is equal to 0.61 lambda by A. So why is this important? So we can now, this is your x1 is your azimuthal, right? You have in the imaging plane, right? This is my azimuthal or x, this is my z, right? So x1 is the width, that is what we are after. So in terms of original diameter, so A is what? Radius I said, so diameter is 2A. So your d width, so your width, right, it is trying to focus. So this was your transducer, there is a lens, this lens is trying to, so it is diverging, right? It would have diverged before, it will be like this parallel, right, and then it will diverge. This is what we had before. We wanted to have this divergence to be less by having a transducer of larger dimension, but if you do that, you will not have, you will have more area. So what we did is we have a lens now which is reducing this, try to reduce it as small as possible, the width, it will be as small at focal length, right, FL, at FL we will have the shortest width, which will be D. So because the geometry, if you see, x1 was only one direction, so but here 2 times x1 is your width. Clear? So if that is the case, I can get my beam diameter. So this will be my beam width. Some for circular transducer, you can get beam width to be this parameter. Okay, so the idea is, if I can have a lens, I could reduce the beam width. So I could have a larger transducer, I can use a lens, I can reduce my beam width. So you may think, okay, maybe we have achieved both, so we are good. Unfortunately, life is not that simple. There is going to be a trade-off. We will just appreciate that trade-off in the next slide. So what, to complete what we have done, this is a transducer, you have a lens, acoustic lens in front of it. So left to by itself without lens, this would have been, the beam would have travelled like this and then gone like that. Now because of lens, I have tried my best to reduce this. Ideally you want only one line, this has to be as narrow as possible, right? If this is without any divergence, if you can go like this, that is the best, but that is not practical. So we have tried to minimize this as much as possible. Of course, it is minimum and it starts to diverge again, inherent. So maybe there is a region around the focus where it is still less than what it would be without the lens. So having a lens still helps. This is the best case, but neighboring also there is some help. So until, right, so this is called as depth of focus. like how much can you retain the focus, the depth over which you can retain the focus, that is your depth of focus. So, if you notice, if I start be aggressive, or I have a lens, right. So, I can make I can change the radius of curvature, right, to make sure that I can have as small as possible. So, I can do all that, but then your depth of focus, so that is the trade off. So, I could shape this up, I could make it as narrow as possible. So, I could start with a big large dimension transducer and have a lens, right, so that I can be very stingy, I can make it as small as possible. But the downside is, the more I push with a large transducer and acoustic lens to minimize, get the tightest focus, as you would say, the problem is it will start to, the depth over which you can maintain that will reduce. So, now you see the problem, there is a trade off. So, if I want to do imaging, right, I want to do imaging, it is a trade off, right, whether I want like this pattern, right, or can I live with little wider, but it will probably stay focused for a. So, it depends on, it is a trade off, it depends on what you are imaging. So, if for example, I am interested only in object, two objects that are there, then maybe I will use the tightest. But if I have several objects at different locations, I would like to make sure that I see all of them reasonably well. So, it is a choice that you have to make. Okay, so, it is a trade off. Okay, so what we will do here is, this kind of completes what I wanted to complete until instrumentation and the imaging physics part of it. So, you notice now we have not really covered the imaging aspect. What we have covered is, you will need a transducer, and if you excite a transducer, this is the field pattern that you will get. So, now how will I use this transducer, right, which has some field pattern, how will I use that to image a region, how will I image this region, that is what we are going. So, we know what is the signal that we are getting, right, we got the equations for the signal. Now, what we need to do is, we will have to organize our material in the context of what do I want to image and how do I want to image. Okay. In that sense, we will jump into the image formation, image recon, that will be our next target. Once we do that, image quality, in this module we have actually kind of combined it, because lateral resolution, axial resolution we already are combining. So, in some sense the image quality, and then we talked about side lobe, main lobe. So, we will not explicitly have a image quality of ultrasound separately. The next module, right, the next topic of how to use this understanding to do image formation in ultrasound is going to be kind of a very interesting, because all this physics is fine. How do you see and how do you interpret the image that you are getting? You are tuned to see some ultrasound sonograms, right? What is that? I mean, how do we connect whatever we have studied so far to what we think when we see ultrasound image looks like? What does it mean there? That connection is going to happen in the next couple of hours max, right? That's when we'll anticipate to complete this topic. So far we have covered as per plan the instrumentation as well. Okay, so we'll jump into image formation next. Thank you.